Aim. Air also has pressure. The weight of the atmosphere pressing down on the earth is known as air pressure. Try this experiment to feel the force of air pressure.
Requirements: sheet of newspaper, table, ruler. Procedure: spread the sheet of newspaper so that one edge of the paper runs along an edge of the table. Smooth it down so that it is flat. Slip the ruler under the center of the newspaper so that it is sticking out about 3 inches over the edge of the table. With your hand, slap the exposed end of the ruler. What happens? Set up the newspaper and ruler again. This time, press your hand down on the ruler slowly. Now, what happens? Conclusion:
It is very hard to lift the paper off the table by slapping on the ruler because air pressure is pushing down on the newspaper and holding it in place. When you press on the ruler slowly, air gets underneath the paper and equalizes the pressure. The newspaper moves easily. Aim. Have you stabbed a raw potato with a straw?
No.
Then you can impress your friend in school by demonstrating the power of air pressure.
Requirements: raw potato, 2 plastic drinking straws. Procedure: place the potato on a hard surface such as a table. Hold the first straw vertically a few inches above the potato that neither opening is covered. Holding the potato in place with one hand, try to stab it with the straw. The straw will crumble and have little effect on the potato. Hold the second straw vertically a few inches above the potato. This time, cover the top opening with your thumb. Try to stab the potato again. Conclusion: compressed air is air that is squeezed into a small space, such as a straw. Compressed air provides a lot of force because it is more dense and is under greater pressure than the air outside the straw. The air trapped inside the second straw made the straw strong enough to actually stab the potato.
Aim. Another interesting property of matter is that no two things can share the same place at the same time.
Requirements: balloon, empty 2-liter soda bottle. Procedure: push most of the balloon down into the bottle. Then stretch the neck of the balloon back over the opening of the bottle. Try to blow up the balloon by blowing air into the mouth of the bottle. Conclusion:
The balloon will not inflate because the bottle is already full of air. Air is made up of matter, so two volumes or quantities of air cannot occupy the same space at the same time. The air that is already in the bottle has nowhere else to go because the balloon is blocking the opening. Consequently, no new air can be added because there is no room for it. Aim. Do you know why birds and aeroplanes do not fall down under the force of gravity? Things that fly rely on lift to escape the bonds of Earth's surface. Let's perform an experiment to see what this lift is.
Requirements: scissors, notebook paper. Procedure: cut a strip of notebook paper about 2 inches wide and 8 inches long. Hold the paper horizontally in front of you, with one of the ends near your mouth, nearly touching your lower lip. It will naturally curve downward. Take a deep breath, then blow steadily over the strip. What happens to the loose end? Conclusion:
As you blow over the paper, the air above it starts to move faster than the air below it. The air molecules moving across the top of the paper spread out and the air becomes thinner. This means that the air pressure above the paper is less than the air pressure below it. The slower, denser air below pushes upward and the paper rises. This is called lift. Aim. Let's study the properties of light. Kids, when you look at the moon, you're not seeing the moonlight, but the reflected light of the sun. This experiment will show how it works.
Requirements:
Fist-sized ball of clay, table that is in a corner, hand mirror, flashlight.
Procedure:
Place the clay on the tabletop. Press the handle of the mirror into the clay so that it stands up facing you. Darken the room by turning off all the lights and closing any curtains or blinds. Stand at a light angle to the left or right of the mirror. Turn on the flashlight and direct the beam of light at the mirror. A circle of light will appear on the wall next to the table.
Conclusion: The light from the flashlight is reflected off the surface of the mirror and onto the wall. If you aim the flashlight straight into the mirror, the light is reflected straight back at you. When you aim the flashlight at the mirror from an angle, the light bounces off the mirror at the same angle and hits the wall.
Kids, can we fill in water in an already filled glass of water? Aim.
To determine the surface tension of water. Requirements: clean dry drinking glass, water and 15 pennies. Procedure: Fill the glass with water so that the surface of the water is even with the rim of the glass. Lean down so that your eye level is at the rim of the glass. Carefully add pennies one at a time. How many pennies can you add to the full glass of water? What happens to the water level? Conclusion:
In water, molecules near the surface have a tendency to cling to each other, creating a stretchy skin called surface tension. The pennies you add take up space in the glass, causing the water to bulge up at the top. The surface tension stretches as much as possible, but finally breaks when there are just too many pennies in the glass. Kids, you can dazzle your school friends with this amazing experiment on surface tension. Aim.
To determine the surface tension of water. Requirements: glass pine jar, cotton handkerchief, rubber band, water, bowl. Procedure: cover the jar with the handkerchief. Push the handkerchief down into the jar slightly to create a well. Then secure it with a rubber band. Add water to the jar through the handkerchief. Pull the edges of the handkerchief down so that it is tight across the top of the jar. Quickly turn the jar upside down over a bowl. If the handkerchief is tight and you turn the jar quickly, the water will not spill. While you are still holding the jar upside down, run your finger across the handkerchief. What happens? Conclusion?
The stretchy skin that forms near the surface of water, known as surface tension, helps keep the water from flowing out through the many tiny openings in the handkerchief. When you run your finger across the handkerchief, you break the surface tension and water pours out through the handkerchief. Aim. Have you heard of cohesion and adhesion? Sounds a lot alike, isn't it? But in this experiment, you will see that they are actually quite different.
Requirements: spoon, food coloring. You can take any color. 1/4 cup water, shallow dish, eyedropper, rubbing alcohol. Procedure: with the spoon, mix a few drops of food coloring into the water. Pour just enough colored water into the dish to cover the bottom. Use the eyedropper to place 1 drop of rubbing alcohol in the center of the colored water. Conclusion:
Cohesion is the tendency of a substance to cling to itself. Adhesion is the tendency of a substance to cling to other things. Water is cohesive, so it has a tendency to cling to itself. It will not adhere to the rubbing alcohol. Instead, the water pulls away from the alcohol, forming a ring around it. Aim. Let us see how detergent disrupts the surface tension of water.
Requirements: large bowl, water scissors, piece of lightweight cardboard, dishwashing liquid. Procedure: fill the bowl nearly to the rim with water. Cut a small triangle from the cardboard, about 1 inch wide on each side. Cut out a small notch on one side of the triangle. This is your boat. Gently lay the boat flat on the surface of the water. The notch should be near the edge of the bowl. Carefully place a drop of dishwashing liquid in the water where the notch is. Watch the boat take off. Conclusion:
The molecules of the dishwashing liquid are attracted to the molecules of the water. This attraction disrupts the cohesion of the water molecules. When you place a drop of dishwashing liquid on the water, it breaks the surface tension, causing a ripple effect that forces the boat forward. Aim. Do you remember the experiment on capillary action? If not, let us perform one more experiment on capillary action.
Requirements: newspaper, small bowl, water, food coloring. You can take any color. Spoon, white cotton handkerchief. Procedure: spread a sheet of newspaper on a flat surface. Fill the bowl halfway with water. Then place it on top of the newspaper. Add 6 drops of food coloring and stir with a spoon. Roll the handkerchief tightly into a tube. Place 2 inches of one end of the handkerchief in the colored water. Let the rest hang over the side of the bowl onto the newspaper. After 15 minutes, remove the handkerchief from the water and unroll it to see how much of it is wet. The food coloring will make it easier to tell. Conclusion:
Cloth absorbs or soaks up water through a process called capillary action. The tiny fibers of the cloth have small spaces in between them. Water molecules move through the spaces by adhering to the fibers. As the water molecules move farther up the handkerchief, they attract and draw up other water molecules below. Aim. The next experiment is based on sensitivity of human touch.
Requirements: 3 small bowls, very warm water, very cold water, water at room temperature. Procedure: fill one bowl with very warm water, one with very cold water, and the last with room temperature water. Place one hand in the warm water and the other in the cold water for about 30 seconds. Now put both hands in the room temperature water. The hand that was in the warm water will feel like it is in cold water, and the hand that was in the cold water will feel like it is in the warm water. Conclusion:
Temperature is the measure of how hot or cold something is. The human body is not always accurate when judging temperature. In this experiment, the temperature of the water that it was in originally influences the feeling in each hand. Aim.
Does anybody know your lung capacity?
No, what is that?
Take a deep breath. Try this experiment and see for yourself. Requirements:
1 gallon plastic milk bottle with no cap, large plastic tub or container, water, straw with a flexible neck.
Procedure:
Fill the bottle with water. Then fill about 3/4 of the tub with water. Set the tub on a flat surface. 2. Hold the bottle over the tub. Cover the mouth of the bottle and flip the bottle over. Put your hand and the neck of the bottle in the water-filled tub. Then remove your hand from the mouth. Make sure the mouth of the bottle stays underwater. Bend the straw's flexible neck and insert the short end into the mouth of the bottle. Take a deep breath and blow into the straw.
Conclusion:
The air from your lungs enters the inverted bottle and forces the water out. Your lungs hold a lot more air than is in the bottle, but you never breathe it all out at once. Aim. Can you tell me what our heart does?
Supply blood to our body.
Correct. Can you tell me how many times it pumps?
No, how can we find out?
You can tell how many times it pumps each minute by taking your pulse.
Requirements: pea-sized ball of clay, toothpick. Procedure: place your hand palm side up on a flat surface. Press the ball of clay onto your wrist about an inch below the base of your thumb. Insert the toothpick into the clay so that it stands upright. Observe carefully as the toothpick twitches slightly back and forth. If it doesn't move, shift the clay until you see the toothpick twitch. Count the number of twitches that occur in 15 seconds, then multiply that number by 4. Remove the clay and toothpick. Run in place for a minute. Repeat step 1, 2 and 3. Is there a difference in your heart rate? Conclusion:
Your heart beats a certain number of times each minute. Everyone's heartbeat is different, but children average between 80 and 130 heartbeats per minute at rest. With each beat, your heart pumps blood throughout your body. you can feel your pulse as each wave of blood passes through the blood vessel located just below the skin of your wrist. This movement causes the toothpick on your wrist to twitch. Exercise rises the rate of your heartbeat. Your heart beats faster in order to pump blood to all the hardworking muscles in your body. The toothpick on your wrist probably twitches more often after you exercise. Aim. Let me show you a trick. You can't always believe what you see. Sometimes your eyes play tricks on you. These are known as optical illusions.
Requirements: sheet of construction paper, tape. Procedure: roll the paper into a tube big enough to look through comfortably with one eye. Tape the paper so that it will not unravel. Look through the tube with your right eye. Keep your left eye open and look straight ahead. Place your left hand against the far end of the tube with the palm facing you. Move your hand slowly a few inches from the end of the tube. Stare straight ahead as you do this, not at your hand. What do you see? Conclusion: both of your eyes face forward, so your field of vision overlaps. This is called binocular vision. The brain tries to blend what each eye sees into one image. In this case, the left eye sees the hand and the right eye sees the hole. The brain perceives this as a hand with a hole in it.
Aim.
Sometimes the moon looks larger when it appears at the horizon. Is it really larger or is it an optical illusion? Requirements:
Flat piece of glass from a picture frame with the edges taped for safety. Marker or crayon.
Procedure:
As the moon appears just above the horizon, hold the glass at arm's length in front of you and trace its shape on the glass with the marker. After the moon is high in the sky, hold the glass at arm's length again and look at the mirror. It will fit perfectly into the circle you drew earlier.
Conclusion:
Although the moon may appear larger near the horizon, it is just an optical illusion. Sometimes your brain judges the size of an object by the size of other familiar objects around it. When the moon is low, there are plenty of objects for your brain to compare it to, such as trees, houses, or hills. High up in the sky, there is nothing else to compare it to. So, you perceive its size more accurately.
did you all enjoy learning super simple experiments?
Yes, Maya. Maya, Vayu, we are very thankful to you for teaching us these experiments, as we carry them in our day-to-day life but were not aware of them.
Don't worry, kids, we are here to help you. Any one of you has any more queries?
No, Maya. No, Vayu. Bye, Maya. Bye, Vayu. Bye.
So, kids, enjoy your party and hope to meet you soon.
Bye.
So great is the world in which we live. It has so much to give, so much to give. There is so much to know while we grow. Lots of things to